Hi, everyone. So welcome to the session on quantum random oracle model. So we'll have 4 talks. And the first one is on the impossibility of time lock puzzles in the quantum random oracle model. It's from Aftin Afshar, Kai-Min Cheung, Yaoxing Xie, Yaoting Lin, and Mohammad Mahmoudi. And Yaoting Lin will give the talk.
Thanks for the introduction. Yeah, so I'm Yaoting, and today I'm going to talk about some impossibility results of time-lock puzzles. And this is a joint work with Aftin, Kai-Min, Yaoqing, and Mohammed. So to begin, I will talk about what I mean by time-lock puzzles, or TLP. So it's a primitive that were first proposed by May in 1993, and then constructed by Rivest, Shamir, and Wagner. So basically, it's a primitive that allows us to encrypt to the future. And since in this work, we are proving negative results, so we'll focus on the following simpler form of time-lock puzzles. So first, it has a generation algorithm that encrypts a classical solution S into a classical puzzle P. And the solver's algorithm should be able to decrypt the puzzle to recover the solution S. And it's important that there's no key shared by the generator and the solver. So given a puzzle, all we need is time to solve it. Yeah. And there are some properties of the time-lock puzzle. So first, the puzzle generation should be fast. It should be immediate. And then the puzzle should not be too hard. It should be solvable in a mild amount of time, like 20 years. And for security, the solution shouldn't be revealed before some future date. And because the adversary might have many computers, the security should hold even against parallel computation. So parallel computation shouldn't get large advantage over the honest user. And there are some known constructions of time-lock puzzles. So Rivest, Shamir, and Wagner gave the first construction by using sequential exponentiation, which relies on their ISA assumption. And Bitansky gave another construction by randomizing coding, but it requires indistinguishability obfuscation. But both of them require public key assumptions, which are quite strong. So we might ask if we can get time-lock puzzles from some weaker assumptions, such as symmetric key primitives. So it's natural to think about the random oracle model, because random oracle model implies symmetric key cryptography. And furthermore, everything in the random oracle model is information theoretic. So it's a clean model to define the notion of parallel time. In the random oracle model, the complexity is measured by the number of queries, and the adaptivity is measured by the number of rounds of queries. In order to make the problem still meaningful, the algorithm can only make polynomially many queries in each round, because otherwise it can just query the whole oracle. Yeah, so for example, a time-lock puzzle in the random oracle model might look like this. So it may need n queries to generate, and n to the 10 sequential queries, or n to the 9.9 rounds of parallel queries to solve, which means using parallel queries won't help you too much. But unfortunately, there was an impossibility result by Mahmoudi, Moran, and Baudin in 2013. They show how to break any time-lock puzzle in the random oracle model by only using low adaptivity. And since random oracle is one-way and collision-resistant information theoretically, so the impossibility results in the random oracle model will rule out black box constructions in the standard model. So it will imply black box separations between time-lock puzzles and the wave function or collision-resistant hash functions. And in the future, it's very likely that we will have powerful quantum computers. So the quantum random oracle model for QROM is a more realistic model. In QROM, the user and the adversaries can make short position queries to the oracle and perform quantum computation. So all of them become more powerful. And what about the existing constructions in this model? So for the first one, as we know that quantum computers are really good at factoring. So the first one doesn't work. And since we still don't know how to construct post-quantum I/O from standard assumption, so the second one doesn't work either. But what if we want to construct time-like puzzles right now? So a more desired form will be time-like puzzles with a classical generator, which is achievable by current technology, and the quantum solver in the future. And in such a setting, since the solver is more powerful, so we could potentially generate harder puzzles. So here's the main question we would like to answer in this work, is whether we can construct time-like puzzles in QROM with a classical generator and a quantum solver that are secure against quantum adversaries. Yeah, however, in our work, we gave a negative answer to this question. And now I will give an overview of our results. So we have two negative results. For the first one is the following. So for any time-like puzzle with classical generator and quantum solver that needs queries to generate, we show how to break them by using order n rounds of classical queries with constant probability. So if you think of the adversary can decrypt the ciphertext with constant probability, then the encryption scheme is totally broken. And for the second one, we focus on a specific type of time-like puzzle, which are perfectly correct. So being perfectly correct means the solver can always decrypt the puzzle correctly. And for such time-like puzzles, with either the generator or solver being quantum, we show how to break it by using exactly n rounds of classical queries. And furthermore, the success probability is 1. And it's worth mentioning that both the attacks only require classical queries to the random oracle. And it's tempting to extend our attack to the quantum generator, quantum solver setting. But we also have a barrier result to our attack. So we show that assuming Everson unbiased conjecture is false, then there is a puzzle with quantum generator and solver that needs exponentially many classical queries to solve. So in other words, this means if we want to prove the impossibility for the quantum generator, quantum solver setting, a quantum query attack is necessary. And finally, we also have a positive result. We show that there is a perfectly correct time-like puzzle that needs 1 round to generate and need at least n rounds to solve. So that means there's a linear gap between the generators and the solver's adaptivity. And this puzzle is indeed optimal. So, and our attack in result 2 is tight. Yeah, so in the rest of my talk, I will sketch the proof of our results. So for our first negative result, I'll recall a simple attack in V13. So the attack is the following. So suppose given the puzzle P, if will first initialize two empty sets S and L, where S is used for storing solutions, and L is used for storing query answers she learned from the oracle. So basically, it will repeatedly run the solver's algorithm in her head, conditioned on the puzzle and her current knowledge about the oracle. And then she will store the solution in this execution to the solution set. And then she makes queries on the query set of this execution to the true random oracle. And then update the list according to the response she gets. And after enough times of iterations, it will take the majority of the solution set as per output. So why does this work? So let's first look at the efficiency. So notice that if only makes make parallel queries in each execution. So the adaptivity is order n. And importantly, this is independent of the number of the honest users queries. And suppose if does not discover any generator's query, then essentially if has sample a view that is consistent with the generator's view. So by the correctness guarantee of the timeline puzzle, if is likely to get the correct solution. But since if can discover queries in at most n rounds, so in most of the execution, if will get the correct solution. Yeah, so take a majority would work for if. Yeah, so now let's move to the quantum solver setting. And the attack is similar. And since it is information theoretic, so she can still run the quantum solver's algorithm many times in her head. But the question now is, what should if asked to the true random oracle? Because now the query set of the quantum solver is not well defined. And even one quantum query can access to the true random oracle. So our idea is to define the notion of heavy magnitude queries. So the notion of query magnitude has been used to prove that Grover's search is optimal. And very roughly speaking, query magnitude reflects the algorithm's knowledge about the oracle on certain inputs. And on the other hand, the notion of heavy queries has been used in proving black box separations. So in this work, we combine these two notions to define the heavy magnitude queries. So a query is epsilon heavy if its query magnitude is at least epsilon. And we can show that the number of heavy queries is at most m over epsilon, where m is the number of the honest users queries, and epsilon is some inverse polynomial. So there will be at most polynomially many heavy queries. So the attack is efficient. And we further observe that if the set of heavy query and the generator's query set are disjoint beyond L, then using the 1-to hiding lemma, we show that if we'll get the correct solution with a high probability. And we also notice that using standard techniques, we can run the attack in quantum polynomial. Yeah, and here's the second negative result. So if we focus on perfectly correct timeline puzzle with either the generator or solver being quantum, then we can further improve the round complexity of the attack. And this would improve the query complexity of the attack in MME 13, even in the fully classical setting. Yeah, so now I'll explain the idea behind our attack in the classical setting. In fact, our attack is inspired by the certificate complexity versus the decision tree complexity in Boolean function analysis. So the attack is the following. So as long as the solution hasn't been fully determined yet, if we'll sample a solver's view conditioned on LP and S first. So here S first means the lexicographically first remaining solution. And then if we'll query the true random oracle on the query set of this view, and then update the list. So basically, if we'll repeat these procedures until the solution is fully determined. And this relies on a crucial observation. So for every query set Q of the solver and every query set of the generator with a solution different from S first, we can show that they must intersect beyond L. And this is because otherwise there's a chance of decryption error, which will violate the perfect correctness. So there will be at most n iterations, and the query complexity is n times n. And let's move to the content generator classical solver setting. So the setting might be less natural because the solver should be the more powerful party. But still, we found the techniques is interesting and it might be useful for other applications. And actually, the previous attack still works, but the analysis is different. So to prove our theorem, we need to use the compressed oracle technique by Zandri. So at a very high level, the compressed oracle technique says that if we write down the joint state of the content algorithm and the random oracle in a Fourier basis, then the state can be written as a superposition over polynomial size databases. So we have a similar observation is that for every query set Q of the solver and every maximum database of the generator must intersect beyond L. Because similarly, if not, perfect correctness will be violated. So there will be at most n iteration and the query complexity is the same. And we also consider a dual setting where the generator is quantum and the solver, the generator is classical and the solver is quantum. And the analysis is similar, so I'll skip the details. And for the Berry result, if the Emerson unbalanced conjecture is false, then we show there is a time-like puzzle that is classically hard. So constructing any such classical query attack will imply a proof for a conjecture. So this means attacking such a time-like puzzle requires quantum queries. Yeah, and here's a sketch of the proof. So in the work of Austrian et al., they construct a key agreement that is secure against classical queries, assuming a conjecture is false. So if the generator and the solver can share a key by querying the random oracle, then they can simply XOR the solution by their shared key. But this is by definition, the time-like puzzle is non-interactive. So we cannot use this theorem as a black box. So in this work, we tweak the previous construction to get a non-interactive key agreement where we use the standard Gorak-Levin hardcore bit and the replications. And we also leverage the fact that the reduction is information theoretic. So once the generator and solver share a key, they can simply use it to encrypt S. And finally, for our positive result, In the work of MV13, they have this pseudo-chain puzzle. So basically, the solution are n+1 random points in the domain. And the puzzle is the following. So basically, we'll use the ith coordinate, the hash of the ith coordinate to mask the i+1 coordinate. So classically, it's easy to see that solving it needs at least n rounds of queries. And this puzzle has perfect correctness. And there's a linear gap in adaptivity. So in this work, we show the exactly same construction is also secure against parallel quantum queries. So which means our attack in result 2 is tight. And here's a sketch of how we prove it. We observe that the solver can win only if there's some collision among x0 through xn, or the solver makes a lucky guess, which means there is some index I such that the ith query hits some solution in the future for some j strictly greater than I. And if none of the events happen, then we show that the solver can only make a random guess. And we formalize this intuition by constructing hybrids carefully. So basically, we use these hybrids to decouple the puzzle and the oracle, coordinate by coordinate. Yeah. So there are still some open problems. So first is that can we construct an attack that really uses quantum queries? And the second one is, can we use a quantum puzzle to bypass the barrier in our work? Because at least when the puzzle is quantum, the attacks in this work won't work. Because in our attack, it needs to run the solver multiple times. But each time, she will consume a copy of a quantum puzzle. And due to no cloning, there's no trivial way to copy quantum states. Yeah. So I think it's a good time to stop, and I'm happy to take any question. Thanks.
Thank you for the talk. Are there some questions?
Can you go to one of the first slides and actually show which one? So.
Which slide?
One of the first. Yeah, okay. Yeah, I remember now. So what I don't understand about this is that you prove that sorry, you did not in the first attack that you showed, you only needed a classical computer, right? And you can already break the puzzle in ON time.
Oh, so for our first attack, it needs to be have quantum computation power, but only make classical query.
So
Thanks.
So she can use a quantum computer, but she cannot make any quantum query. So it's in the random oracle model, but she has infinite amount of computation.
Yeah, so if it's free to make quantum queries, but is that in our construction, we don't know how to utilize this power. Yeah.
Is there another quick question? So let's thank the speaker again. The following talk is towards compressed permutation oracle, and it's given by Dominique Leroux.
Hello. I guess I need to speak at this one. Hello, and welcome to my talk. I will be talking about compressed permutation oracles and so I will be talking about compressed permutation oracles, and since you may not be all familiar with those things, I will first talk about quantum random oracles, what they are, although probably most of you know. Then go to the compressed function oracles, so the thing that was mentioned in the previous talk, also the result by Jean-Pierre, but I will give a little bit of a slightly different view on the technical details. Then compressed permutation oracles, so what are these things, why do we need them, how do we find them, and then the main result towards compressed permutation oracles. So I will not show that they work, but I will show some result one step towards this. So what is the quantum random oracle model? The quantum random oracle model is an analog to the random oracle in classical cryptography, which is a heuristic for modeling hash functions. So when you have a proof that involves a hash function, in many cases it is very difficult or impossible to prove certain properties that are actually that seem quite intuitive and natural. And the random oracle model allows us to get around this by just replacing the hash function by a completely random function and saying, okay, we just analyze that. And in the quantum random oracle model, we take into account that the adversary is quantum and therefore can do so-called superposition queries, which I've drawn here. My apologies for the formulas because it turned out to my surprise that PowerPoint on Android does not have a formula editor, so, but it has a pen, so that's what you get. So the quantum random oracle model allows us also to query a random function h, but we do these superposition queries, which means that the adversary just gets access to a quantum gate UH, which maps the basis states cat x, cat y to cat x, cat y XOR hash of x. So that's the normal way of evaluating a function quantumly, and that's how we model the quantum random oracle model. The next slide, please. And well, while the quantum random oracle model gives us a good heuristic, it is unfortunately also a lot harder to use in proofs than the classical random oracle model. Well, not the classical pure ROM, the classical ROM. There are a bunch of techniques that have been developed. So there are these small range distributions, which are a useful trick. Then one way to hiding was already mentioned in the previous talk once. We have two Q-wise functions, which are a nice trick. We have that random functions are indistinguishable from random permutations. And in particular, we have the compressed oracle technique, which was also mentioned in the previous talk by Jean-Pierre, which is a very powerful, but also rather difficult to understand technique for doing proofs in the quantum random oracle model. And this technique is what this talk will be based on. So this much introduction to about the quantum random oracle model. Now I will try to give you an introduction into the compressed oracle methodology. So before we can go, so this is basically based on what Jean-Pierre already developed, but in my paper I'm like defining things differently, in my opinion, a bit nicer, but that's of course arguable. But I will present you my view. And the first step towards defining the compressed oracle, which is a technique to like write the oracle in a way that can be where you can keep track of queries and so on. We will see that. But before we can get to that, we understand an intermediate thing called by Jean-Marie the standard oracle. And the trick in the standard oracle is that we do things a bit differently than in the random oracle model. In the random oracle model, we, at the first step, just pick a random function h, and then allow the adversary to do superposition queries. But the function h is probabilistically chosen and then determined in the very beginning. In the standard oracle, we keep this function h in superposition. So we don't pick one function, but we just initialize some registers with the superposition of all possible functions, and then run the adversary in superposition between all the functions that might be chosen. So more precisely, for each input x to the random oracle, we have a separate register hx that contains the output h of x to the random oracle. And the trick is that we don't like in the classical view, we would just probabilistically pick something and just store it in that value. So the output hx will be stored here. But we don't do that. We just initialize each of the hx's with this state cat star, which is defined to be just the superposition of all possible values. I'm omitting normalization factors here. So each of the hx's is just initialized with the superposition of all possible values initially, and then by adversary queries it can collapse, but initially that's what it is. And when we do when we let the adversary do a query, we don't have just the registers x and y, so that the y register gets changed to y XOR h of x, but instead we involve all those registers here. And the query that the adversary is allowed to do is defined by saying if each of these hx registers has some output value small hx, and we have cat x in the input register, then we XOR hx onto y. So the x determines which of those is XORed onto this. So to maybe make it more clear, I drew a little picture of a circuit here that's supposed to illustrate this. So we have initially the registers h1, h2, h3. So this is a random oracle with only 3 possible inputs, a very small one. They are all initialized with equal superposition. And then when we make a query, and let's say the x register that the adversary controls, so x and y are controlled by the adversary, the h registers are hidden away from the adversary. So if the adversary, for example, puts cat2 here, then this wire gets XORed onto y. And this keeps the whole random oracle in superposition between all possible values, unless the adversary has, for example, measured the output. So why is this useful? Well, the first important fact is this is indistinguishable still from access to a random function. So while this definition is a bit weird, or at least more complicated, it's perfectly impossible to distinguish this from the random oracle, so we can just replace it. And no, not yet, sorry, one back. And another important thing that will become a bit more detailed in the later steps is that so you have this particular state cat star, that means nothing is known. And if the adversary, for example, makes a query, this cat star becomes something else. It becomes, for example, 5, if the adversary has measured that there's 5 there or something like this. So this standard oracle already has this property of keeping track of what has been queried. Although it's not in the nicest possible encoding, we can already see that information theoretically, this thing somehow tracks what is queried. Next slide. And to get like better access to this hidden power of the standard oracle, we introduce another trick into our oracle. So now we come to the compressed function oracle, often just called the compressed oracle, but since I will distinguish it from permutation oracles later, I will call it the compressed function oracle here, or short CFO. And To understand the CFO, we introduce one more operation that I call decomp1. Decomp stands for decompression, and 1 stands because it's the operation that we apply to just one wire. But it's just think of it as some nice operation that decompresses. And what we define is some operation that maps cat bottom. So we assume we have one more state in our space. So our registers can contain bit strings, but they can also contain a special symbol bottom. And we map this special symbol bottom to cat star. Remember, cat star was the superposition of all possible bit strings, while any cat x is mapped to itself. Ignore this plus small for now. Now, if we don't have the plus small here, such an operation does not exist, or at least cannot be unitary, because you could get this cat star also by mapping this superposition of these. Like if you map cat star, it would be mapped to cat star, and cat bottom would be mapped to cat star. So that would be forbidden. And therefore, in order to actually have such an operation, we need to put in like a little error term, and then it works. So the details of this can be done in different ways. In Gendry's paper, it involves various Fourier transforms. I found that they are not actually needed. So in my presentation, it works without Fourier transforms. But I don't want to get into that. The main message to take away here is that up to small, but in the technical analysis, very annoying errors, bottom is mapped to the superposition of everything, and x stays x. So how do we use that? Well, remember the oracle before had an initial state that had cat star everywhere, superposition of everything. Now we initialize our oracle with cat bottom everywhere. But that means that if we want to do a query, I can so if you want to make a query, before we had cat star and would apply this circuit. So now we have cat bottom, so we apply this decompression and make cat star out of it. And then we apply our query. So now we have the oracle output in superposition on these wires. Then we XOR it onto the output. And then we apply the inverse of this to undo it for the next query. So each query decompresses, meaning this bottom goes to stars, does the query and recompresses. So that's the basic step. And now it should be almost obvious that this is indistinguishable from the standard oracle, because all we do is we apply this to make it into the state, the initial state of the standard oracle. And then after each query, we undo the decomp and redo it. So it is just by elementary analysis the same circuit. So this is the definition of the compressed oracle. But why do we do these weird compression, decompression stuff? Well, there are various features of the CFO. So the first feature is that any query done by the adversary only changes the one H output that is queried. So if we look again at this, so if X is, for example, cat2, then only this wire can be affected, because here we have decomp and decomp inverse, and they cancel out. So whatever you do, you will only affect one of the oracle registers. Although, sorry, confusing the direction. You can be in a superposition between different places, but you will always affect only one of them. So the consequence is that the superposition, that the function, that these hx are always in a superposition between many states, and that they are all cat bottom, except in a small number of registers. So if you make a query, you could write down the state of the whole oracle. I would do a superposition of states, and each state would be something like cat bottom, cat bottom, cat bottom, 5, cat bottom, cat bottom, cat bottom, 7, and so on. with at most q, which is the number of queries, places that are not q. And a value table with lots of bottoms you can think of as a partial function. So we have now a partial function in this huge list of registers hx that represents what has been queried so far. And this has two advantages. First, we have an efficient representation of the state of the oracle, because a partial function of size q can be efficiently represented. And second, we have a log of the queries. We know, or we know in superposition, so we could measure, but that would be bad because we would destroy things. So things are not always that easy. But in principle, we know what the adversary has queried and what the adversary hasn't queried. So these are the great features of the CFA. Okay. So now, one side note, just because we need to understand that for later, is the distinction between two things that I call the use view and the make view of the oracle. So these are two different use cases. So use view means that I use the CFO in an analysis where I have some construction, say for example an encryption scheme, and this encryption scheme uses a hash function as a building block, and to analyze this building block I use the compressed function oracle. While the make view is a situation where, for example, a construction that implements a random function, for example, let's say the Lubry-Rakov to implement an
It's from Aodong-Jiang, Jima, and then Feng-Jiang. And Aodong-Jiang will give the talk.
Hello everyone, I'm Pierrick Méaux from the Laboratory of Network Cryptography Technology. This talk should be given by Aodong-Jiang, but he cannot come here due to the time conflict. So I will help him present his work. This presentation consists of four parts. First, I will introduce the background. Paper-Hellman-Key exchange is a fundamental and elegant cryptographic scheme. EHK exchange is widely used to establish an ephemeral session key in cryptographic protocols such as TLS signal. However, EHK exchange is insecure when the adversary owns a quantum computer due to the famous Peter-Shaw algorithm. Due to Shaw's quantum algorithm and recent advances in quantum computing, there has been an increased interest in post-quantum cryptography, PQC. The goal of PQC is to design classical cryptographic systems that remain secure in the presence of a quantum adversary. Recently, NIST launched a post-quantum crypto project and published a call for submissions of quantum-resistant public key cryptographic algorithms, including PKE, digital signature, and CAP. CAP consists of three algorithms. Key generation algorithm, which on input lambda generates PK and SK. Encapsulation algorithm, which on input PK output session K and the corresponding ciphertext C. And the decapsulation algorithm, which on input SK and the ciphertext outputs session K. CAP is mainly used to establish a session K. Take Alice and Bob as an example. Alice runs the key generation algorithm and obtains PK and SK. Then Alice sends PK to Bob. Then Bob runs the encapsulation algorithm using PK to obtain K and the ciphertext C. And then sends this to Alice. Finally, Alice runs the decapsulation algorithm using SK and C to obtain K. Thus, based on CAP, two parts Alice and Bob can establish a session K. August 24, 2023, NIST posted the first CAP standard draft CABR, FFPS 203. CABR is a lattice-based CAP with INDCCA security. INDCCA security is a standard security notion and taken as a target security NIST call for proposal. Roughly speaking, we say a CAP satisfies INDCCA security if for any PPT adversary, the key generated by honestly running the encapsulation algorithm is indistinguishable from the key that is randomly generated from the session key space in the view of the adversary. The CCA means that the adversary can additionally query the encapsulation oracle. Currently, the IND CCA secure CAM is mainly constructed based on the FO-like transforms that transform a weakly secure PKE to an IND CCA secure CAM. In FO-like CCA secure CAM, the encapsulation algorithm usually randomly picks a message M from the message space and encrypting M using the randomness that deterministically generated by GM. And the session key is computed by HMC for all HM. The decapsulation algorithm will verify the validity of the ciphertext by re-encryption. On the one hand, re-encryption is decapsulation makes it an expensive operation. As shown by HV22, when re-encryption is removed, there will be a 2.17 times and 6.11 times speed up over decapsulation in CABR and PhotoCAM. The re-encryption makes the CAM more vulnerable to side channel attacks, and almost all the NIST PQC round 3 CAMs are affected. The side channel protection of re-encryption will significantly increase deployment costs and thus complicate the integration of NIST PQC CAMs. For ephemeral key establishment, one has to move the current DHK exchange to post-quantum CAMs. IND1 CCA security is required for such a substitute CAM in post-quantum TLS 1.3. CAMs TLS, post-quantum signal, and post-quantum noise. IND1 CCA security is the same as the IND CCA security, except that the adversary is restricted to make at most one single decapsulation query. Obviously, IND1 CCA security is implied by the IND CCA security. However, the current IND CCA secure CAMs require re-encryption, in particular at CCS 2020. Schwab, Spillet, and Wiggers take the design of the dedicated IND1 CCA secure CAM as an open problem. At Asiacrypt 2022, Dumitin and Wardney shows transforms TCH and TH can turn a CPA secure PKE into an IND1 CCA secure CAM. Different FO-like transform TCH and TH doesn't require re-encryption. TCH is basically the reactor transform with the asymmetric part. In RCH, the ciphertext consists of two parts. One is the encryption of a random message M, and the other is a tag of a message and ciphertext, also called key confirmation. The session key is derived by HM. TH is similar to TCH, except that the tag is removed, but the key is derived by HMC. The constructions TCH and TH are based on an idealized model called random oracle model ROM, where a hash function is idealized to be a publicly accessible random oracle. In post-quantum setting, quantum adversary can execute hash functions an arbitrary superposition of inputs. Therefore, at Asiacrypt 2011, Bourne argued that to prove post-quantum security, one needs to prove security in the quantum random oracle model, QROM, where the adversary can query the RO with the quantum state. The security of the TCH was proved in the ROM with techniques epsilon r is approximately equal to big O with 1 over Q, epsilon A, where Q is the number of the queries to the RO made by the adversary. Epsilon A is the advantage of the adversary A against the CCA security of the resulting CAM. Epsilon R is the advantage of the reduction against the CPA security of the underlying PKE. The security of a TH was also proved in the QROM with the techniques epsilon r is approximately equal to big O with the input 1 divided Q cubed epsilon A squared. The security of the TH was proved in the ROM with techniques epsilon r is approximately equal to big O 1 over Q cubed epsilon A. The QROM proof of TH was left open. Both TH and TCH do not require re-inclusion, but compared with TCH, TH doesn't meet the K conformation and thus will not lead to separatist expansion. The following is our results. First, we prove the security of TH and its implicit variance TRH in both ROM and QROM. TRH is the same as the TH except that in decapsulation, a pseudorandom value H with the input star C is returned instead of an explicit abort for an invalid separatist C, such that decrypt with the input SK and C equal to the abort. TRH is essentially the construction U cancel park in HHK 17, except that the secret seed S is this decapsulation is replaced by a public value star. Here the star can be any fixed message. In fact, our proof can work for both secret seed and the public value thanks to the newly introduced decapsulation simulation technique, while the current IND-CCA proofs for implicit FOCAMs can only work for secret seed. We choose to replace secret seed by public value since it reduces the secret key size and makes the construction more concise. Moreover, from a high assurance implementation point of view, public value is also preferable to secure seed. This is our reduction tightness result. In Rome, our reduction has tightness epsilon r is approximately equal to big O 1 over Q epsilon A, which is much tighter than the epsilon r is approximately equal to big O with the input 1 over Q cubed epsilon A given by HV22 for TH. In the QROM, our reduction achieves tightness epsilon r is approximately equal to big O 1 divided Q squared epsilon A squared, which is tighter than epsilon r approximately equal to big O 1 divided Q cubed epsilon A squared given by HV22 for TH with separatist expansion. In particular, our QROM proof will not lead to separatist expansion. Then for TH, TRH, and TCH, we show that if the underlying PKE means malleable property, big O 1 divided Q loss is unavoidable in the ROM, and big O 1 divided Q square loss is unavoidable in the QROM. That is, our ROM reduction is optimal in general. Roughly speaking, the property says that an adversary can efficiently transform a separatist into another separatist with decrypts to a related plaintext. In particular, such a malleability property is met by real-world PKE schemes. Finally, we compare the relative stresses of IND1CCA and IND-CCA in the ROM and QROM. For each pair of notions AB and the IND1CCA ROM and IND-CCA ROM, QROM and IND-CCA QROM, we show either an implication or separation, so that no relation remains open. Next, we show our main techniques. In our paper, we first prove the security of TRH, and then show that the security of TRH can reduce to the security of TH. This is our QROM results. We show the IND1CCA security of CAM based on TRH can be reduced to the IND-CPA security of the underlying PKE. the IND1CCA security of TH can be tightly reduced to the IND1CCA security of TRH. These are the concrete security reduction forms. For any adversary B against the IND1CCA security of attempt, we need to contrast a reduction A that runs B as a subroutine to break the INDCPA security of the PKE. Since B can make queries to the random oracle H and the decapsulation oracle, thus A needs to simulate the H oracle and the decapsulation oracle for B. The main technique here are the simulation of the decapsulation oracle and the embedding of the hard distance. Re-encryption is the core feature of FO-like CCA camps, which guarantees that only specific valid ciphertexts can be currently encapsulated, and thus makes the decapsulation simulation in the ROM or QROM proof easily. Removing re-encryption makes the current decapsulation simulation for FO-like CCA camps incompatible with the camps in this paper. For valid ciphertext C bar, such that decrypt with the input SK C bar equal to M bar, not equal to abort. The decapsulation returns H M bar C bar. If we reprogram H M bar C bar to a random K bar, we can simulate the decapsulation of C bar using K bar without knowledge of SK. To guarantee the consistency between the outputs of H and the simulated decapsulation, one needs to correctly guess when the adversary makes the query M bar C bar to H and perform a reprogram at that time. In ROM, a randomly guess is correct with a probability 1 divided Q. If in the QROM, due to adversary's superposition RO query, it is hard to define when the adversary makes a query M bar C bar. We find that the consistency between H and the simulated decapsulation can be guaranteed if the predict decapsulation with the input SK C bar equal to H M bar C bar is satisfied. This scholars shows that the random merit and the reprogram can keep the predict satisfied with a high probability. However, the standard merit and the reprogram in DFM 19, DFM 20 cannot be directly applied to our case. This is due to the fact that the random merit in these papers is performed for all the H queries, while in our case, there is an implicit classical H query used in the real decapsulation that will be removed in the simulated decapsulation and thus cannot be mirrored. Extending the mirror and reprogram technique, we drive a variant of mirror and reprogram, which is suitable for our case. With the new mirror and reprogram, the QROM adversary can accept simulation with a probability at least big O with the input 1 over Q squared. Roughly speaking, the standard mirror and reprogramming shows that the probability of an oracle quantum algorithm outputting a tuple xz such that the predictor is satisfied can be bounded by the probability of that an algorithm SA runs A to obtain xz such that the predict is also satisfied. In particular, S will randomly mirror and the reprogram on all the SH queries. In our extended version, the probability corresponding to SA is divided into two terms. One is the probability of that S1A runs A to obtain xz such that the predict is also satisfied. S1A randomly mirror and reprogram on all its H queries, except for one specific classical H query X. The other term is the probability of that S2A runs A to obtain xz such that the predict is also satisfied. S2A is an algorithm that randomly mirror and reprogram on H queries after A makes the specific classical H query X. In the security proof of TRH and TH, the second term is negligible. This is a lemma that shows our extended memory and reprogramming technique. The second technique is about the embedding of the hard instance. In our paper, we use the one-way-to-hiding technique to embed the instance of the underlying IND-safely secure experiment. One-way-to-hiding technique has several variants, such as the general one-way-to-hiding, the semi-classical one-way-to-hiding, double-sided one-way-to-hiding, and mirror rewind mirror one-way-to-hiding. In our case, we choose the double-sided one-way-to-hiding, since in our case, the variant gives the tightness bound, and the mirror rewind one-way-to-hiding cannot use here, because such a one-way-to-hiding is incompatible with the mirror and the reprogramming technique. In our paper, we need to guarantee the advantage of an algorithm searching a reprogramming point in double-sided oracle, thus we additionally develop this lemma. Here is our conclusion. An IND1CC is sufficient to replace Stefan-Hellman in the post-quantum migration of the widely deployed protocols, such as TLS 1.3, signal and noise. Our results show that IND1CC secure CAMs can be constructed in the ROM and QROM without re-encryption and separate expansion. Compared with IND1CC secure CAMs based on FO transform, the IND1CC secure CAMs based on TH and TRH do not require the re-encryption in decapsulation. The re-encryption is highly vulnerable to attacks, and its side-channel protection will significantly increase deployment costs. Thus, from the protocol point of view, removing the re-encryption of FO-like CAMs will improve the performance of embedded side-channel secure implementation. Therefore, according to our results, one can easily transform Cabal PKE into an IND1CC secure and CAM without re-encryption and separate expansion, and then establish post-quantum secure variants of TLS 1.3 and noise with Cabal signal and noise with better performance in the embedded implementation. That's all the presentation. Thank you. And for some professional questions, Holden Jiang glad to for email.
Thank you for the talk. So for the question, you can send it to the email, and we will thank all the speakers of the session. Now we have a coffee break.
Some words for the talk.
Zero knowledge. Big zero knowledge.